Okay, exam two. Overall, everyone did quite well. There's a few questions, well, sorry, four specific questions that seem to get hung up a little bit. And what's interesting is they all had something in common. So this is good to review because maybe there's some parts in my lectures that I did not emphasize well enough, and I can catch up on that right now. So let's go through them. So the first question is, which of the following is not used to determine drag force acting on the cyclist? What this question is really asking is, do you know the equation for drag force? I've listed the equation down here. That was not part of the question. F drag is equal to 1/2 rho CdA V squared. You need to know this equation, and you need to know the parameters in the equation. Rho is density of the fluid. CD is the shape of the object and how well the fluid moves over the object. A is the frontal area of the object that's perpendicular to the flow of the fluid, cross-sectional area. And V is the velocity of the fluid moving over the object. So now we just need to pick out from these answers which one of those answers is not in the equation. Frontal area is, that's the A. Density of the fluid, that's the rho. Velocity of the cyclist, that's not in the equation. Velocity of the fluid moving over the cyclist, that is in the equation. And that is something that I tried to emphasize in the lecture on drag force. So it might be worth going back and taking a quick look at that video again, because this comes up when we start talking about drag force and drafting in cycling and in swimming in particular, and a little bit in running. In fact, if you watch the sub-2 attempt by Eliud Kipchoge, he was drafting off the car. The car was trying to get the fluid moving, and then the drag resistance acting against him would be less because the fluid, even though he's running faster, the fluid is already moving, the air is already moving. And that's the whole idea behind drafting in cycling or in swimming, is you're getting behind someone where that person is moving the fluid, and therefore the resistance force due to drag force is reduced. And same thing, if you're swimming downstream, that's an easy one, because your velocity relative to the land is much faster than the velocity of the fluid that you're moving through in the opposite direction. So your resistance force is less relative to your land speed. Okay, so you got to know drag force equation. All right, second one, in a kinetic analysis of running, which force do you not include in the equation sum F equals ma? You should know this equation, Newton's second law. What we need to do is add up all the forces acting on the object. And when we do that, we get the product of mass of the object times the acceleration of the center of mass of the object. Mass is a measure of an object's inertia. Inertia is resistance to change motion. And we quantify that with the units of kilograms. A is the acceleration of the center of mass of the object, not the acceleration of any particular segment of the object. It's the center of mass. And the sum of the forces on the left-hand side of the equality sign, we just add up all the forces acting on the object. Newton's third law tells us for every force acting on an object, there's an equal and opposite force created by the object. We do not put the by forces into this equation when we do a kinetic analysis. That's the mistake a lot of people will make, is they'll add the force acting on the object and force created by the object in this equation, and that's incorrect, because they're equal and opposite to each other. So they would always add up to zero, which would mean that you would always have zero acceleration, which means you would only have constant velocity, which means you could never go from zero velocity to something. Therefore, you'd never have movement. You only put the by forces, only put the on forces into this equation. So now we just need to know that and look at the answer. So the force of the ground pushing on the person, yes, that goes in the equation. The force of the person pushing on the ground, no, that does not go in the equation. The force of gravity acting on the person, yes, that goes in the equation. So the force of the person is what we often want to know, but we don't actually put that in this equation. We put the reaction force, Newton's third law, into that equation. And that reaction force is the ground reaction force. And that's where we do what I call mental gymnastics, because we want to know the force of the person pushing on the ground. Well, we're not actually using that force in this equation. We're actually using the reaction force, because we can measure the reaction force using a force platform or scale. Okay, so that's just putting together Newton's second and third law. Below is an illustration of the vertical ground reaction force during running. Up is positive. I always try to give you the reference frame. At which points or point would the acceleration of runner's center of mass be negative? All right, so what I'm asking again here is how to do a kinetic analysis. In this case, kinetic analysis of running. So over here on the right-hand side, I put some additional information. This was not as part of the question. We have sum of forces equals MA. Sum of the forces acting on the object equals the product of mass of the object, measure of an object's inertia, resistance to change motion, times the acceleration due to the center of the center of mass. And we have two forces acting on the runner. And this is the kinetic analysis that we've gone over in class. So this is running on the level. And we've got gravity pulling down, so up is positive, so that's a negative force. And we've got the ground reaction force pushing up. And in this picture, I've decomposed the ground reaction force, which is in 3 dimensions, into a vertical component and a anterior-posterior component. We then pick a direction that we're interested in. In this case, we're interested in vertical. So we only have 2 vertical forces acting on the runner, gravity and ground reaction force. We add up those 2 forces and we get the product of mass times acceleration of the center of mass. All right, so now let's look at the figure. And it's always important when you see a chart is to look at what's on the y-axis and what's on the x-axis. On the y-axis is ground reaction force in units of Newton. And on the x-axis is time in seconds. And you've got the fairly standard ground reaction force. I've talked about the impact peak that we see early on, typically in running. A lot of times in sketching it, we don't sketch it out simply because it's hard to know that that's going to be there. But that's the neat thing, and that's why we measure ground reaction forces, because our sketches are often sort of robust guesses in terms of what we're going to see. And you see I got a dotted line there for body weight, okay? That's the force of gravity acting on the runner. So now we have all the information we need to answer this question. We've got 2 forces acting on the runner. We're looking for where the acceleration of the center mass would be negative. So we just need to look at this equation. So wherever the acceleration will be negative, wherever body weight is greater than the ground reaction force, wherever this value is greater than that. So if this is 100 newtons and this is 1,000 newtons, this side has to be negative 900 newtons. So what we need to do is find on this plot where the ground reaction force is less than body weight, or the body weight is greater than ground reaction force. Here's body weight. We've got 1 point that's less than body weight. So this is the answer. Acceleration will be negative when the ground reaction force is less than body weight. Okay, last question. Below is an image of swimming velocity versus time. The figure includes velocity relative to the left and right arm strokes, as well as the combined left and right effect on swim velocity. During which phase, A, B, or C, would drag resistance forces be greater than drag propulsion force? So again, we're using Newton's second law here. We're doing a kinetic analysis swimming. We've got velocity versus time. And this is the plot, or this is the data that we're interested in here, where velocity of the center mass is illustrated during a swim stroke. So we have slowing down, speeding up, slowing down, speeding up, slowing down. So let's do a kinetic analysis of swimming. This is one of our figures that we worked with the kinetic analysis of swimming. And these are the forces acting on the swimmer. We're only interested in the horizontal motion. So step 1 of the kinetic analysis, identify forces acting on the object. Step 2, pick a direction. And in this case, we're interested in the horizontal direction. So we only deal with horizontal forces. So I've got drag resistance and I've got drag propulsion as horizontal forces. Add up all the forces acting on the swimmer in that dimension, and we get the product of mass of the swimmer times the acceleration of the center mass in that direction. So we have two forces, propulsion, which is going to be positive, and resistance, drag resistance will be negative. So what are we looking for? The figure was during which phase would drag resistance forces be greater than drag propulsion force? So here's drag resistance, here's propulsion. Wherever this is greater than that, this side of the equality sign will be negative. Mass is always going to be a positive number. So acceleration has to be negative. So how do you have a negative acceleration? Well, velocity versus time, when you see that plot, the slope of the velocity versus time plot is acceleration. So what we're looking for is anywhere where the slope is negative will tell us a negative acceleration. This will be a positive acceleration, positive, negative, positive, positive, negative. So I gave you three choices, and what I'm really asking you to look at is to identify where acceleration will be negative because of the relationship between these two magnitudes and the directions. So the answer is A. Okay, so those are 4 questions that were a little bit of a stumbling block. They're all built around understanding Newton's second law and how to do a kinetic analysis. So hopefully this video helps explain that a little bit more. And maybe go back and watch a couple of the videos on kinetic analysis of each of the sports and see if you can pick up some of the details a little bit more. And feel free to shoot me questions, and I'll be glad to either try to answer in email or to meet up on a video call and explain in more detail. Okay, thank you.